When I do give Zoom talks, I prefer to write in real time because I think that slide talks are sometimes put speaker into too much of temptation to sort of to rush over things. But this particular talk I always give with notes because it has a diagrammatic calculus that simply makes it impossible to finish a talk within an hour due to the time it takes to draw diagrams. So I sort of apologize for this being essentially a slide talk. So this is, and also let me say that this is a joint work with Adam Genge and Clemens Koppensteiner, who were both postdocs in Oxford when we all sort of met and discussed this project. Adam is now in Budapest. Clemens, unfortunately, has left mathematics. But sort of, as I will tell you, the project very much sort of lives on and evolves. So essentially, it's a categorification story. And the goal is to sort of to understand and appropriately categorify the Heisenberg algebra. So I'm not by any means sort of a theoretical physicist, so you'll have to take my word for it that in quantum mechanics, a sort of a finite dimensional version of this algebra arises. But if you sort of take a very natural generalization of it, you arrive at this basic object, which has been sort of in play for quite a while. So we call it infinite dimensional Heisenberg algebra HK, where K is our base field. I will always work about a sort of a closed, algebraically closed field of characteristic 0. So you define this algebra via generators. It has generators which are traditionally written as AN, where n is integer. And A of 0 is the identity, the multiplicative identity of the algebra. And this is a free algebra generated by this, these generators over K with the relation that commutator of AM and AN is the delta function of n minus m times m. So basically, unless one of these numbers is negative of the other, the corresponding generators commute. So, and if they don't, then they commute up to m times a0, m times identity. So this means, and this is a useful perspective to take, that we can think of this algebra as the ring of differential operators on a polynomial ring over K in infinite number of variables. And we think about this by thinking of AN for positive n being the partial differentiation with respect to variable xn, and AN for negative n, or a minus n for positive n, is n is just multiplication by n. So if you do that, if you and you can check that these are precisely the relations between these operators. So if this differentiates with respect to xn, this multiplies by nxn. And then if you sort of, you can check that they satisfy these relations. You can check that these are precisely sort of the these are more or less precisely the. So this part is responsible for the ring itself, for the variables in the ring itself, and this part sort of the you can think of one half of the generators as the differential operators, and the other half as variables themselves. And this leads to the very basic sort of accompanying idea to that of Heisenberg algebra. We always consider, when we talk about Heisenberg algebras, we always talk about their Fock space representations. So notice that if you have this ring of differential operators on this ring, then this ring itself is, of course, a representation of it. These guys act by normal multiplication, and these guys act by differentiation. And this representation is reducible and faithful. Are there any questions? Can I check that you still hear me? Because sometimes Zoom freezes, so every 5-10 minutes I'll ask whether I'm still talking to an audience.
Yeah, I can
Good.
still hear you.
I mean,
I can't.
it's just
We can't see you. Is that intentional?
that's quite intentional.
Okay.
I'm not interested in mathematics. Is interesting. So I mean, I've had experience of giving talks and lectures where I would speak to 20 minutes for 20-30 minutes into as I realized later emptiness because Zoom has froze. So now I will regularly stop and check that this is not happening. So this is sort of the classical presentation of the Heisenberg algebra HK via these generators. Let me give you a different presentation, different set of generators with different set of relations. And the reason I give you this alternative presentation is that that's the presentation we'll need to work with in our work. And the reason for that is that somehow when we move on from this simple case to the case of Heisenberg algebra defined by a lattice, which means free abelian group with a form on it, then this presentation will only exist if the form is symmetric. And morally, our lattice is numerical K group of a derived category, and our form is Euler form. And of course, unless it's in full generality, it's not symmetric. So unless you're on Calabi-Yau. So therefore, we need to work with non-symmetric forms, and that means that this definition is simply not available to us. However, this one is, and in a moment you will see explicitly. So where does the sort of the form and lattice come in? Just for the record, HK is this basic Heisenberg algebra, is Heisenberg algebra of one-dimensional lattice, so just integers z with an obvious pairing, which could be thought of a K group over a spec K of a point. So when we talk about this algebra, we sort of geometrically think ourselves as sitting on a point, the simplest possible variety. So the generators are now called Pn and Qn for positive integers. So it's seemingly sort of a similar set to this. And the relations are that all P's commute and all Q's commute. Now, P's and Q's, if you multiply Q to this sort of Qm by Pm, this is not quite, I'm not saying power because this is very much, don't be confused by this notation. This is not nth power of P. But as we'll later see, in a sense, this is an antisymmetrical power of P, but that's much later in the categorified context. So for the moment, it's just sort of the way I write the index of this generator. Don't confuse this with the power. So when you multiply Qm by Pn, what you get, so that's the only sort of significant relation, so let me try to explain it. What you get is you take a sum from I equals 0 to the minimum of m and n. And the sum goes Pn minus I, Qm minus I. So the simplest way to get a feeling for just look at the example. So if you multiply Q3 by P2, you start by just swapping them around case I equals 0. So the sort of just the commutation, P2, Q3. But then, whereas in this presentation, you gained sort of m times 1, in this presentation, you get this sort of full tail. You get Q2 minus 1, P 2 minus 1, Q 3 minus 1, and then P 2 minus 2, Q 3 minus 2. So essentially, you just, to compute Q and Qm and Pn, you just swap them, and then you add all the sort of successive terms where both powers drop by 1. And in order to understand how these two sets of generators are related to each other, it's not straightforward. So the easiest way is to do it in terms of generating functions. So if you take sort of generating functions of Pn generators, that's the same as if you take the generating function of a minus m, so a negative integers generators, and add this divide through by m, and then you exponentiate it. And then similarly with q, but now you take the generating to get the generating function of qn, you take the generating function of positive ams divided by m, and then exponentiate it. In particular, p1 is a minus 1 and q1 is a1, but higher terms are the relation is a lot more complicated. Fortunately, none of this talk will concern the relation between these two types of generators. So this is simply what we're not going to work with. And in these terms, as before, you obtain the Fock space representation by killing all the qn's. So you sort of kill what used to be your positive part of the positive an's, the differential operators, and then you're just left with just the ring. So that's the basic story I want to tell you so far of the sort of the algebraic object. It starts with sort of Heisenberg algebra of over a field, Heisenberg algebra over a point, as it is sometimes called. And the important thing is that this is what's called Heisenberg relation, because that's the only relation you impose on these generators to get the algebra. But when you reformulate it in terms of this alternative set of generators, your Heisenberg relations becomes slightly more complicated. It becomes this sort of sum with decreasing powers of your p's and q's. So, are there any questions before I move on? Good. Can you guys still hear me?
Yeah.
Perfect. So now let me talk. Let me talk about the natural generalization of that, which is of the most interest to us. Because to make this from algebraic object sort of geometric object, we want to learn to associate Heisenberg algebra to ideally a variety, and we're going to do this by associating Heisenberg algebra to the numerical K group of the derived category of variety, which is a lattice. There is a theorem by Taboada saying that numerical K group, provided you are on something smooth and proper, is a abelian group with a form on it. So this is our sort of setup for this definition. M is free abelian group of finite rank. Chi is a bilinear form. Then I'm going to define the Heisenberg algebra of this lattice as follows. The generators are now, again, sets of sort of Pn and Qn for positive integers n, but now they're also indexed by elements of the lattice. So there is a P and a Q for every n and for every element of the lattice. And the relations are P0 and Q0 for any element is just the multiplicative identity. As before, P's commute, all P's, even for different sort of A and B's commute, and all Q's, even for different A and B's commute. Then there is this crucial relation, which sort of allows us to express Pn for any sort of sum of two elements in terms of the P sort of lower indexed P's for both summands. So essentially, this tells you that you only really worry if you have a lattice with some set of generators. Then the generators of your Heisenberg algebra will be P's and Q's indexed by the generators of the lattice. There is sort of this relation is, if I have time and end, I will tell you that sort of upgrading this relation. So basically, even for what we're trying to sort of to take this project to at the moment, we need to be able to give a similar definition for a vector space with a bilinear form. And for a vector space, sort of additivity is not enough. You also need to come up with a formula for what is a scalar P of a scalar multiple of an element. And of course, this should be compatible with taking an integer multiple of an element. So then you have to look at what does this formula tell you about an integer multiple of A, and that's a sort of separate and rather interesting story.
I have a question.
Yes.
When you were spelling out these relations, is the fact that M is a free abelian group of finite rank important? Is the finite rank?
How should I say it? No, for the relations, sort of it isn't.
Okay.
I mean, you should. Nothing stops you from imposing these relations and on a free, sort of on a lattice of an infinite rank.
I see.
However,
yes,
however, whether what you will get will make any sense, sort of is a separate story.
Okay.
So now here is the Heisenberg relation that we had before. But now observe that to commute Qn via Pm, we once again have a sum from 0 . Here's a formula. Hello?
Yeah, I think you're.
Sorry,
Yeah.
Just a moment, let me go back and try to share my screen again. It just told me, fortunately, I think Zoom improved because now it told me that the recording stopped. Can you see my screen again?
I can see your screen.
When did my screen stop broadcasting? What should I repeat?
5 seconds ago, but also before the screen went, we couldn't hear you for about, let's say, 10 seconds.
Yeah. So what was the last thing you could hear?
So I asked that question about, and then you answered it, and then I think right after that answer.
Right, great. So, so now I just have to explain to you the sort of the relation, the Heisenberg relation, the form it takes in case of a lattice. And again, this concerns commutation of Q, N, and PM. And again, to commute Qn past Pm, you start with Pm and Qn, and then you take the decreasing power sum. At each term, you decrease both powers by 1 until you run out of one of them. But if before all the coefficients were 1, that's the previous relation we had. Then here, the coefficients are non-trivial, they're not 1. And they're, in a sense, when you drop both powers by I, the coefficient is ith symmetric power of Euler form related in A and B. And let me explain this. I don't, of course, mean to take symmetric power of an integer. However, the formula is that what I call S I of an integer r is 1 over I factorial, r plus I minus 1, and so on, decreasing all the way down to r. And what the meaning of this is that when r is positive, this is the dimension of an of ith symmetric power of r-dimensional vector space. And when r is negative, this kind of thing doesn't make sense. But this formula, but this is the sort of the number you should take. This is numerical formula which matches this when r is positive. So in particular, observe that when chi AB is 1 in particular, then all the symmetric powers have dimension 1, and sort of there we are. This gives you all the coefficients here being 1. Because on on the lattice of rank 1, you only need to take one element, which is the generator of the lattice, and the form is a standard one. So Euler pairing of A and A is 1, and therefore all these numbers are 1, and we recover the previous case. Observe, however, also that if the Euler pairing between two numbers is 0, then all Q's marked by A and P's marked by A commute with all Q's marked by B and P's indexed by B, sorry. So in particular, as I mentioned before, the sort of basic Heisenberg algebra is Heisenberg algebra of one-dimensional integer lattice with which pairs 1 and 1 to give 1. So are there any questions? Good. Can you guys still hear me?
Yeah, sure.
Now you maybe you can see why I keep asking this question. So I mean, I'm very impressed because before Zoom didn't warn you that something has went wrong.
Yeah.
So now let me now tell you about the sort of a result which is in a sense special for me because in mid-90s when this result sort of happened, I was a sort of first-year student in Cambridge, where Ian Grojnowski was, and during my time there in sort of first, second, third year, I kept hearing that Ian has proved this amazing result, and at the time I didn't really know enough mathematics to appreciate even or understand what this result was, but it was sort of a humbling moment when we started working this project and realized that I'm in serious danger of writing a next chapter in what once upon a time when I was a first-year student seemed like really, really complicated maths to me. So this is a rather beautiful story which brings geometry into it. So suppose X is a smooth projective surface. Let X square brackets n be Hilbert's scheme of endpoints on X. So specifically when X is a surface, this is a smooth variety, which is a resolution of the symmetric quotient, where you take nth product of X and factor it out by action of the symmetric group. So this is a theorem which is proved by Ian Grojnowski and Hirako Nakajima independently in the 90s. And this is not quite how it's stated in their papers. However, this is the result essentially reformulated in the language of what I've just told you now. Warning, by H star of X, I mean the rational cohomology with rational coefficients of X. That is not integer lattice of finite rank. So we need to take this as a vector space. So for this, you need the definition, which is in progress at the moment and should appear in the final sort of revision of this manuscript, which is the Heisenberg algebra of the Heisenberg algebra of a vector space with a bilinear form, finite dimensional vector space. However, this, in a sense, don't sort of without nitpicking, conceptually, this is what happens. What happens is that Heisenberg algebra of the rational cohomology of X acts on the infinite sum, on the sort of total cohomology of all Hilbert schemes of all of Hilbert schemes of endpoints for all n. And not only this Heisenberg algebra acts, it identifies this with the Fock space. So the sort of the Hilbert schemes of endpoints on X form in the rational cohomology the Fock space for the Heisenberg algebra of the rational cohomology of X. So in order to do this, you need to construct sort of these operators. You need to construct Pn and sort of Qn of the sort of some element of rational cohomology, and then of course show that this and what essentially happens is that they sort of Ian and Hirako do this. They construct these operators and then show that they satisfy the Heisenberg relations. So because their construction is very geometric, and I apologize for the next bit. I don't always give this talk to people who know exactly what derived categories are. So even though the action here happens in the level of homology ring, as we know, the sort of K group Grojnowski ring refines algebraic part of the rational cohomology, and to the K group there's natural projection from derived category. And it was very clear from the start that the construction was done essentially by Fourier-Mukai kernels on products of this Hilbert schemes. And it was sort of immediately reading this, if you're familiar with Fourier-Mukai transforms, you would sort of conjecture that the corresponding Fourier-Mukai transforms would give you sort of functors between derived categories which should satisfy the similar kind of relations. So I think Ian mentioned this somewhere in one of his papers, if my memory sort of, that this should sort of lift to the level of K-theory or derived categories. So finally, and we're sort of getting to the end of this sort of in a sense, history lesson, but also the context for this project. Next, in a sense, this is a sort of was a fundamental wow result, which was sort of very well published and became very famous. There are two ways you can try to generalize it. One, you can ask, can you generalize this away from surfaces for any smooth projective varieties? Secondly, you could ask about to categorical level. And the first direction was done by Andreas Krug. So who following sort of well-known results of Hyman and Bridgen-King-Reid, the sort of what's called Hyman Bridgen-King-Reid equivalence, which states that for a smooth projective surface X, derived category of the Hilbert scheme of endpoints is equivalent via essentially Bridgen-King-Reid type correspondence with Sn equivariant derived category of the nth product of X, which is by definition the derived category of the quotient stock, where we take Xn and divide it by the action of Sn. So this Xn divided by Sn is normally a very singular space. Xn is its, for X projective surface, is its resolution. But the stock, however, is smooth. So what we're saying is that there is a singular space, and there are, in a sense, two resolutions. One is geometrical, which is the Hilbert scheme of endpoints. And the other is sort of, in a sense, algebraic. We just take the smooth stock, which sort of corresponds to it. And unsurprisingly, the two are derived equivalent. So if you try to generalize this result for higher dimensional X by looking at Hilbert scheme of endpoints, they're horrible. They're not smooth, and in a sense, they're a wrong thing to take here. However, so when X is threefold or higher, this is no longer smooth or nice in any way, and this equivalence doesn't hold. However, this symmetric stock is very much still a smooth sort of smooth stock, smooth geometric object. So Krug has then shown that for any smooth and proper variety of any dimension, the Heisenberg algebra of the Grojnowski group of X acts on the direct sum of Grojnowski groups of symmetric quotient stocks. So this sort of shows that this lifts this result to K-theory. Finally, his action is constructed at the level of derived categories. However, there it's only a weak action, because the Heisenberg relations in this algebra only hold up to isomorphism of functors. And every time this kind of things happens, you ask yourself, should I be looking at the two categorical picture, which means should I be looking at something, should I be keeping track of this isomorphism of factors? Should my algebra have sort of an extra layer of structure which predicts how the sort of the various relations there should hold. And this brings us so naturally to the subject of categorification, because that's sort of, in a sense, one of the things that motivated that whole thing, other than just love for categories, which I think most people who come to this seminar should share. Before I proceed, are there any questions about Andreas's results? Can you guys still hear me?
Yes, we can hear you.
Brilliant. So, what is categorification? I mean, one can give not just talks, but lecture mini courses or just full lecture courses in this subject. But very briefly, the idea is that if we have an algebra A, in categorification we replace vector spaces essentially by categories and linear maps by functors. So an algebra A should be categorified to a monoidal, additive, abelian, or triangulated, whichever context you want to work with, category, whose Grothendieck ring, Grothendieck K group, but of course, if the monoidal structure on A will give you the ring structure on this, is just A. And if you've never seen this before, it might seem strange, why would you want to do that? But the idea is that objects of A, I really mean generating objects. So objects of this category categorify elements, again, in a sense, I mean generating elements of algebra. Monoidal structure on this category categorifies the product in this algebra. And now the key thing is that morphisms in this category A, they encode the relations between the generators in the algebra. So essentially, the morphism structure in this category will give you relations in the K group, which should be the same as the relations between these guys in the algebra. And if this sounds confusing or even sort of puzzling, how can you ensure that? I'll give you a very explicit example in a second. Rather beautiful. I think that's one of the prettiest things I will tell you about in this talk. And then, of course, similarly, if you have an A module M for this algebra, this should be a category M, a monoidal functor from your categorified algebra to the category of functors from M to M, such that this would give K group of M, which in view of this functor becomes an A module. And this should be isomorphic to M in the category of A modules. So again, you should have a category and essentially an action of A on your category, such that on level of K theory, you get just M. Then we say that category M categorifies curly and categorifies module M. And so the second generalization of these results was saying, right, let's try to categorify Heisenberg algebra to sort of write down, to incorporate into our algebra the level of two morphisms, which means, see, the objects, the elements sort of the algebra become objects in your category. And then there is a level of morphisms. So this is a new thing, so sort of morphisms and relations between them in your algebra. And these guys should essentially hold, sort of specify the relations which will hold between the functors involved. So this was done by Mikhail Khovanov, who is the father of this whole categorification business in around 2010, and it was only done for a point, essentially over a point. So this was if Krug was stepped forward to arbitrary dimensions, and Khovanov was in a sense, let's move one up the categorical ladder, but step back all the way from surfaces to just spec K. And this is what he did. He proposed the following additive K-linear monoidal category. Its objects are finite words on symbols capital P and capital Q and their direct sums. The monoidal structure is just concatenation of words. Identity element is an empty word, of course. Otherwise, that's what if your product is concatenation, then your identity has to be an empty word. And now this is the most interesting thing. Remember I said that this is sort of, now we're going to introduce the kind of calculus of morphisms between these guys, which will, on the level of K group, guarantee us the Heisenberg relation. So here it is. The morphisms are oriented planar diagrams. So if I have a source, all my diagrams always go upwards. So here's my source word, PQP. Here's my target word, QPP. And the rule is that these sort of oriented planar diagrams are upwards oriented at P endpoints. So see, here, any strand which goes into P is upward oriented, and downward oriented at Q endpoints. So everything sort of from Q to Q, it goes downwards, from P to P, it goes upwards. So we consider such diagrams up to isotopy, which means continuous transformations. But as usual in this business, I mean, there are a lot of technical jargons here, which I'm sort of sweeping under the carpet, from under which they still try to breathe fire at us. So you are allowed to sort of continuously transform these diagrams, but what you are sort of not allowed to do is to change the type. So you're not allowed to sort of to create new crossings. I could sort of, I'm not allowed to deform this into sort of a loop and then cross this loop with this. You must keep sort of the sort of crossing structure the same. So in addition to these continuous transformations, we impose the following relations. So one is that you can pull apart such double crossing. So if you have sort of Q strand going downwards and a Q strand going downwards, then that's just identity. Now, because I've set up to continuous transformations, this automatically ensures a similar relation for P strands. Why is that? Because take this, right, let's see if I can take this diagram for Q. Roughly speaking, I'll sort of explain this trick once. And now add to it a following diagram. So now it becomes a morphism from PP to PNP. And now, because we're allowed to do isotopies, I can straighten this out. And as I straighten this out, this thing will turn upside down and become essentially just a similar sort of diagram for P's. And of course, if this relation holds for Q's, then after continuous transformation, this will turn into this, and identity will still stay identity. And we'll sort of we'll get the same thing. So let me remove all these things from my talk. But basically, this kind of trick of turning a diagram essentially in any direction by using isotopy allows you to only really need to define these things for Q's, and all the analogs for P's will happen automatically. Second is something that's called in sort of for people who deal with knots and links, is the sort of the pitchfork move. So we can move a strand through crossing. Third one tells us that we've got a P strand going upwards and Q strand going downwards. We can pull them apart as long as P is to the left of the Q. That's just identity. And then we have, however, going in the opposite way. This is not true. If we have a Q strand to the left of P strand, then this is identity. Minus what's called sort of a cup and a cap. This diagram. And you can sort of see that these two together tell you that sort of P and Q, of course, do not commute. And we'll see, sort of in a second, I will show you how Heisenberg relation pops out of it. Then there are relations 5 and 6. Relation 5 tells you that sort of bubble, a sort of a counterclockwise bubble is just identity two morphism of an empty of the monoidal unit of an empty word. So this is a morphism from empty word to itself, and this is just identity morphism. And last one tells you that any counterclockwise sort of curl is 0. So, and composition of such diagrams is given by vertical concatenation. So, are there any questions about these relations? Or so altogether, I've just defined a monoidal category for you. Its objects are words in P and Q, monoidal structures concatenation, and now morphisms are these sort of planar diagrams with source word at the bottom and target word at the top, which obey these rules. Are there any questions about this?
Is this category symmetric monoidal?
No, of course not.
No, right? Yeah.
Precisely because PQ is not.
Exactly.
Is sort of is not isomorphic to QP.
Yeah.
Not even sort of on any sensible level. So now this is beautiful. I don't think I have time to explain this in full detail, but these relations might seem a bit odd, or at least not entirely sort of obvious. This is a bit more sort of familiar ground, but together relations 3 and 6 ensure the following. Consider the following morphisms from QP to the direct sum of PQ and 1. So morphism from QP to PQ is sort of an upward arrow like this and downward arrow like that. That's a valid morphism from word QP to the word PQ. And from word QP to 1, I just have a cap. I just have a cap like this. So together, these two morphisms define the morphism to direct sum. And vice versa. From direct sum of PQ and 1, I have a morphism to QP, which is, again, sort of arrow going like this and arrow going like this. P strand going upwards, Q strand going downwards. And here we have a cup from empty word to QP. So these relations precisely tell you that these two morphisms are mutually inverse isomorphisms. For example, if I compose this morphism with this morphism, I will have a component which goes from 1 to QP, which is a cup. And then I will compose it with a component which goes from QP to 1, which is a cap. So together, I will get this curl, and this curl is identity. So component going from 1 to 1 in this through composition is identity. On the other hand, component going from 1 to PQ is I take this and concatenate it with this. So I have a little cup here, and then this forms me a counterclockwise curl, which is 0. And finally, sort of, if you want to look at the composition from QP to this and then back to QP, then this is going to be essentially this relation. So this is sort of a quick exercise to do. But once we know that these are two mutually inverse isomorphisms, we know that in the K group, product of QP equals to the product of PQ plus 1. This is the Heisenberg relation. Because in a second, I will explain that I think of the capital Q is, its class in K theory will be my Q1. Capital P is class in K theory will be my P1. And here I'm saying that Q1, P1 is P1, Q1 plus P1 minus 0, 1 minus 1, Q1 minus 1. So just this. This is sort of the basic Heisenberg relation. So this is example of how you how you set up your calculus of morphisms in a way that in K theory you get the relations you want. Now, but wait, why am I saying that capital Q is Q1 and what is, for example, Qn for general n? Well, relations 1 and 2 tell us that, give us sort of an action of symmetric growth on an elements on word p n times and q n times. Because this tells us that, if you just write a permutation, then this tells you that the basic transposition is self-inverse, and together with this, it tells you that the sort of this relation will eventually tell you that all that matters in this diagram is not how the arrows go, but the permutation type. So this ensures that if we correspond to a basic transposition in SN, a diagram from PPPP to PPPP, which just has a transposition of neighboring to a couple of P's or neighboring couple of Q's, these guys will obey the relations of the symmetric group. Now, then we send Pth symmetric power of n to be the direct summand of the class in K theory of Pn, given by symmetrizing an idempotent of Sn. Symmetrizing idempotent is 1 over the order of the group plus sum of all elements in the group. This will be an idempotent of Pn, and therefore will define us in K group after completing the respect to direct summands, will give us the element that corresponds, the direct sum that corresponds to that idempotent is this Pn. So this is why I said a while ago that Pn is, in a sense, not the nth power of sort of P1, but the symmetric nth power. So theorem proved by Khovanov in his paper. This assignment that assigning to Pn the direct summand of the nth power of P in the K group given by symmetrizing idempotent of Sn with respect to the action of Sn, which is given by this sort of diagrams corresponding to basic transpositions, and similarly for Qs, give you a map from HK from the Heisenberg algebra. I just, for every generator of Heisenberg algebra, I told you what the corresponding element of K of this ring is. And then you can check that these define a map of algebras. You can check that all the Heisenberg relations are satisfied by this sort of direct summands here, and therefore you get a map from HK to K0 of HK. And so the K group of this monoidal category I've just defined admits a map from the Heisenberg algebra, and this map is injective. So, the moment you prove that the relations, the Heisenberg relations, are satisfied by the images of generators, you essentially get this. And then you, well, sorry, this is my bad. I got carried away. The injectivity, once you prove the relations that are satisfied, you get a map of algebras, and then for injectivity is done via sort of the Fock space representation trick. But I don't have time to explain that now. Ask me a question afterwards if you want to know about that. So this is now, it was conjectured this is an isomorphism. This was eventually proved a couple of years ago, and the proof is sort of a rather technical paper for sort of that works a lot to get this result. So proving surjectivity in such cases is not easy. It's easy enough to show that your object you want to categorify sits inside the K group of your conjectured categorification, but showing they have not introduced any junk is difficult. So finally, I'd like to mention that there is a result by Cautis and Licata in 2010 also. They construct a similar categorification with a very similar calculus for the Heisenberg algebra of an ADE root lattice. So this now brings us to results by myself and my collaborators. So now I can finally tell you what did we do. Before I start on that, are there any questions about sort of Khovanov's categorification? Are there any questions about any of these things that I've told you just now? Good. Can you guys still hear me?
Yes, of course. Yeah.
Right. So our idea was that we want to sort of now go back to Krug's result. What we want to essentially extend Khovanov's result from the Heisenberg algebra of a point to essentially Heisenberg algebra of any smooth projective variety. And we want to get this sort of two-categorical picture. We want to get a sort of a monoidal category whose K group would be the sort of Heisenberg algebra that we want. And then we want to construct a sort of the analog of this Fock space action. We want to show that that our sort of two-categorical object, our monoidal category, that we construct, acts on the essentially sum of symmetric quotient stacks. Remember, sort of to move to the arbitrary dimensional variety, we work with a direct sum of, here it's K theories of symmetric quotient stacks, but we want to replace this by direct categories of symmetric quotient stacks. So we want to essentially we want to construct a two-functor from our sort of Heisenberg two category into the categories of symmetric quotient stacks involved. So I'll make this precise in just a second. So let A be a smooth and proper DG category. So for us, it's a non-commutative smooth and proper variety, essentially. So any DG enhancement of DB coh of X for any smooth and proper algebraic variety X is a smooth and proper DG category. So you get all the, so basically we work, at our level of generality, it costs us nothing to work with non-commutative varieties. We don't have to start with an algebraic variety X, then take its derived category, and then take it with its enhanced structure. We can just sort of take any, doing this will give you a DG category, which will be what's called smooth and proper, and we can just start with that. So second thing is we work in Morita context. So for us, any smooth and proper DG category is enhancement, not traditionally when you talk about DG category enhancing a triangulated category, you want H0, the homotopy category of A, to be the enhancement, to be the triangulated category being enhanced. In Morita setting, we consider A as enhancing the triangulated category, which is the derived category of perfect A modules. Now, one of the reasons to work with DG categories is that if you take symmetric nth power of the dB coh of X, you do not get dB coh of n symmetric power of X, of this sort of symmetric quotient stack. You cannot perform these constructions on plain triangulated categories. But if category A, and this is also a reason to work in the Morita setting. If a category A enhances, DG category A enhances dB coh of some X, then its nth symmetric power of this DG category enhances dB coh of the nth symmetric power of X. And last little technicality is that the derived category of perfect modules over A is the same thing as derived category of perfect modules of what's called H perfect Holloway, which is essentially the category of H projective perfect modules of A. So notice I'm saying something strange. I'm saying that perfect modules over A are perfect modules over perfect modules over A. But this is a standard trick. Essentially, it's sort of homotopy-Karoubi completion. If you have category, so the Morita, essentially working with Morita enhancements, essentially replaces any DG category A by its H perf A. If you've done that, you're in a classical enhancement world, because if sort of H perf of A is quasi-equivalent to H perf of A. So in the taking H perf of A is essentially taking triangulated hull and Karoubi completion. So, but this equivalence shows that for us, from Marita point of view, A and H-perf A are the same enhanced triangulated category. They enhance the same triangulated category. So we can replace A on a DG level by H-perf A. And this gives, by result of Shklarov, us a homotopy Serre function. Essentially, it's a quasi-equivalence from A to itself plus natural quasi-isomorphisms hom A, AB to hom AB, comma, SA dual. Another way to say this is that, we have this quasi-equivalence and this quasi-isomorphisms, and if you take H0, if you pass to homotopy category, you'll get a genuine Serre function of H0A. And any old DG category is not obliged to have something like this, but it's triangulated, sort of taking triangulated hull and Karoubi completion, taking this H-perfect hull, gives you something that has a homotopy Serre function. And now I can finally sort of state our results. So if you've done that, if you've taken a DG category, viewed it smooth and proper, viewed it as a non-commutative smooth and proper variety and replaced it by its H-perfect hull, then there exists a DG2 category, HA, which we call the Heisenberg category of A. I'm actually, so DG2 category means that we've got a two categories such that one categories of morphisms are DG categories. I'm actually lying, I'm sweeping more dragons under the carpet. This two category is not DG-cut enriched, it's Ho DG-cut enriched. It's enriched by the homotopy category of DG categories, which was constructed by Tau, and this is DG categories with quasi-equivalences inversed. So this means that in this guy, the one categories of morphisms are still DG categories, but the functors between them were modified. So sort of composition and everything in this is not given by DG functors, but by DG quasi functors. Again, passing to homotopy level fixes all that. The moment we pass to homotopy level, this difference disappears. So we also have DG, or rather Ho DG-cut enriched to category FA, which is the categorical Fock space of A. Now, unlike this one, this is very easy to construct. This is a two category. Its objects are integers. And we think of every integer as corresponding to M symmetric product of A. The one morphism categories are simply the categories, the DG categories of enhanced functors from SNA to SMA. Two morphism enhanced natural transformations. So as usual, I mean, if this was all algebraic, then I would just say take symmetric nth power of X, and for my categories of one morphisms, take derived category of SNX cross SMX. So derived category, so the category of essentially Fourier-Mukai kernels from SNX to SMX. And we construct a sort of a homotopy lux, so meaning it's a again, it's a strong up to homotopy two functor from the Heisenberg category of A to this Fock space, to this categorical Fock space, which is essentially the action, this Heisenberg action on the categorical Fock space. But notice that our categorical Fock space was constructed out of this symmetric and symmetric powers of the original A. So this corresponds precisely to this story, where the Heisenberg algebra of the K group acts on K groups of symmetric powers of X. So here we have the sort of Heisenberg two category of our A, which is as input, instead of inputting K group, we're inputting A considered as enhanced triangulated category. So we are sort of inputting the enhanced derived category of our non-commutative variety. And that then our construction, Heisenberg category construction, will give us something that will act on enhanced derived categories of symmetric powers of our non-commutative variety. And not only these things exist, but as in Khovanov case, the ordinary Heisenberg algebra of the K theory, numerical K theory of A, of our non-commutative variety, injects into K group of our DG2 category, of our Heisenberg category. So our Heisenberg category on the level of K groups is, well, it contains faithfully the Heisenberg algebra of the original Heisenberg algebra we're trying to categorify. So again, we say that this means that HA categorifies HK0 num A. It might, though, introduce some junk, but our conjecture is that this is an isomorphism. This conjecture we now know to be wrong. There are counterexamples. Basically, the reason for this conjecture to be wrong is that one should not, and this is what we are working on and what occupied last sort of year of our lives, is that one should never have been working in this project with K group. Sort of when you've got a category, you need to decategorify it back to an algebra. And there is taking K group is not the only way to sort of, it's not only additive invariant you can work with. So problem is, a big problem is that the K group does not satisfy Khovanov formula, which when you're working with sort of powers and symmetric powers, you should definitely be sort of satisfying. So one needs to build a whole equivalent of this story where K group is replaced by Hochschild homology, for which the Khovanov formula does hold, and which is a lot closer to the original Nakajima and Grojnowski story, which works with rational cohomology. And then we expect that this conjecture will has a chance of holding. Basically, we have a theorem which says that if for those varieties for which Khovanov formula holds, this is well, rather this is an isomorphism. But so basically, what we have, however, is that we also know that the K group of our categorical Fock space contains in itself the Fock space of the original Heisenberg algebra, and we can prove that if this is an isomorphism, if there's no junk in the Heisenberg algebra itself, then the Fock space also, this map is surjective. So the counterexamples to this we have are precisely in those situations where the Khovanov formula doesn't hold for a variety. So I think I will stop here. The rest is just a quick explanation of our construction of this two category, or rather of the subtleties involved. But the construction is very similar to the Khovanov construction. It uses a similar diagrammatic calculus, but with some problems introduced by essentially homotopy adjunctions not being strict adjunctions. But I think that it will, given that I'm 5 minutes over time already, this would be a good point to start.
Thank you, Timothy. Can we all unmute ourselves and give the speaker a round of applause? Okay, if you have any questions for the speaker, you can ask them now or put them in the chat.
Yeah, I don't see any question. I'm still on my slides, so I don't see anything that's being asked in the chat. So if there is anything in the chat, please read it out.
Yeah, I'll tell you. I was thinking of something. I mean, this is probably a very stupid question, but I'll ask it anyway. So you made this comment towards the end that Hochschild cohomology is
Hochschild homology.
Hochschild homology could be a better fit because of the Khovanov formula. Yeah. But in your theorem, I mean, I also had to look at your paper quickly. So the conjecture is basically saying if the categorical Fock space, if the categorical Fock space categorifies the classical Fock space, sorry, this should be an if and only if with this isomorphism, right? Between.
Just one, let me explain this. We have a conjecture. The conjecture is this injective map is in fact surjective. And our Heisenberg category really categorifies the Heisenberg algebra of the K group of the region A. What we have is a theorem which says that if this is an isomorphism, then this one is an isomorphism as well, because for the Fock space, we can also only show that there is an injection from the Fock space of the original Heisenberg algebra into the K group of our categorical Fock space. So in particular, one way to disprove this conjecture is to demonstrate a situation where this Fock space, where this map is not an isomorphism. Because a theorem says that when this is an isomorphism, this is an isomorphism, so this not being an isomorphism breaks possibility of isomorphism. So indeed, in the new revision of this paper, we construct a counterexample by constructing a situation where this map is not an isomorphism, and we do it because of Q-net formula, because everything here consists of symmetric powers, and then you can K0 over A is simply sum of K0s of symmetric powers of A, and then you do essentially a dimension count. So I mean, I'm not saying that one should not work with K group. I mean, for a variety of reasons, K group is still preferred by many people, categorification, because even constructing a map sort of from the original Heisenberg algebra to the sort of decategorification of the category in case of Hochschild homology is technically complicated. However, because K group is not compatible with Q-net formula, you will get some junk. I mean, at that point, one should stop saying that it's junk and start saying, very interesting then, which classes sort of are then, what are these extra classes in this K group? So by building our sort of, the construction is very natural. It uses the same natural diagrammatical calculus. So it becomes interesting to study the parts of this and the parts of this which do not come from here. So this is one direction. But another direction is saying that if for some reason you really want this to be tight, then you must work with additive invariant, which for which this multiplicative formula, Q-net formula holds, and then you really need to do this for Hochschild homology, which is very complicated, but we are on the verge of finishing it, unless something significant hicks up. I'm happy to say that we now have this theory for Hochschild homology. And this is why we needed, of course, to build the Heisenberg algebra of the vector space, because Hochschild homology is a vector space. I mean, there is, of course, a whole story of finding a sort of a lattice inside there, but that's I don't think that's completed at the current sort of science. So at the current state of our science, we can only treat Hochschild homology as a vector space with a form. Hence the necessity to even define what this is for Hochschild homology. But now that is all done. We can now do that. We can construct a map, fortunately, by functoriality. So what's left is checking that the Heisenberg relations we construct in here essentially when we prove that these relations hold, we need to prove that isomorphism we obtain are functorial in a sense, because then they would extend to our sort of functorial construction of this map. But again, that's this is a work in progress, so I don't think I want to go into technical details.
No, it's okay. Thank you. Any other questions? So the version that I can see on the archive, that's the most recent version?
Yeah, that's the most recent version, although the paper is being refereed, it went through one revision. So in a sense where we've been asked to introduce, so referees were very positive about the paper. The original paper asked us to introduce some revisions. We introduced them. Then the referees sent us another report saying, brilliant, now you sort of have to finish doing Hochschild homology sort of version of this construction, and made some other demands. So now we're working on the essentially version 3 and hopefully final version of this paper. And once our phrase is satisfied, hopefully we will post the revised version to our.
Yeah.
So currently, in the current version, we'll find nothing about Hochschild homology story. This is
that I saw. Yeah.
In a sense, I personally think that Hochschild homology story should have been a separate paper, but for a variety of reasons, our referees did not think so. So now this paper is already long, and now will become even longer.
Okay. Any other questions, anyone?
Yeah, I should